So we're continuing with the filament thing. Where do we leave? It was 4.8,
Wait.
end of 4.8.
4.9.
Okay, cool. So we've got the standard material model described previously. It's a good fit for isotropic surfaces made of a single layer, but multi-layer materials are fairly common, particularly materials with a thin translucent layer over a standard layer. Real-world examples of such materials include car paints, soda cans, lacquered wood, acrylic, and others. So we've got a comparison of blue metallic and then blue metallic underneath a clear coat.
Looks good.
What kind of clear coat is actually on that?
Sorry, Jacob, you're really quiet.
Oh, I don't know, to get louder when I adjust my mic.
Discord has like a mic volume setting, but
I think I have mine at max, so I think
No.
you can adjust my volume if it's too quiet.
you're already 200% for me.
Oh, jeez. Oh man, I hate when that happens. Am I like way too quiet or what?
Just kind of.
It's okay at 200%, I think. Yeah.
Okay, okay. So I was just wondering what clear coat are we modeling with the clear coat model? It's like a layer of wax or something, like acrylic. It just says, oh, it says right there.
Yeah, I guess lacquered wood or acrylic, or I guess car paints do different types of stuff.
I think that it has parameters to it, so you can kind of make like different types of clear coats if you want. I think it's kind of just the generic idea of like having something that only lets some light through and reflects some.
Looking at what they got here, you've got some Fresnel, and then you've got a little bit more specular, and then also some reflection on there. So,
Alright.
yeah, I don't know. I guess that's kind of what we're looking at. Clear coat can be simulated as an extension to the standard material model by adding a second specular lobe, which implies evaluating a second specular BRDF. To simplify the implementation and parameterization, the clear coat layer will always be isotropic and dielectric. The base layer can be anything followed by the standard model, dielectric or conductor. Since incoming light will traverse the clear coat layer, we also must take the loss of energy into account, as shown in Figure 24. Our model will, however, not simulate interreflection and refraction behaviors. So I guess it's basically like you've got two surfaces being considered, I guess.
Yeah, and they are modeling like infinitely thin layers, so that's why they don't model refractions and interreflection.
So we've got the clear coat layer modeled the same as the Cook-Torrance microfacet BRDF used in the standard model. Since the clear coat layer is always isotropic and dielectric with low roughness values, we can choose cheaper DFG terms without notably sacrificing visual quality. Not remembering what DFG is.
Those are like three separate terms, right? The D, F, which is like
okay. The diffuse.
Yeah.
There's the normal distribution, right, of the microfacet.
Yeah.
Fresnel and then geometry, self-shadowing and whatever.
Okay. Love it. Okay.
And the V was just the G term, right? Or it was the visibility. Was that
V is the visibility term. It's the G term divided by something. So,
did it have the Fresnel in it, or was it just G?
It's just G.
Oh, okay.
So, survey of the terms listed in these two papers show that the Fresnel and NDF terms we used already in the standard model are not computationally more expensive than other terms. This other paper describes a much simpler term which can replace the Smith GGX visibility term. It's dependent on the light vector and the half vector, I guess, is that? I gotta pull up the glossary here. I have that available, I think.
Wait, why did they do a quarter divided by L dot H squared in their GLSL version?
Yeah, they don't go into it, I guess. Yeah. It's looking at this one. It's Eurographics presentation, I guess.
It makes sense because you are you are divided by like L dot H square, right? And the quarter is just 104.
Right. Yeah, okay. Yeah, I think that's just my...
So this masking shadowing function is not physically based, but its simplicity makes it desirable for real-time. So in summary, our clear BRDF is a Cook-Torrance specular microfacet model with a GGX normal distribution function, a Kelman visibility function, and a Schlick Fresnel function. And so the GLSL implementation is very simple. So it's just L dot H squared divided by 4. Right, so the Fresnel term of the specular BRDF requires F0, the specular reflectance at normal incidence. This parameter can be computed from an index of refraction of this interface. We will assume that our clear coat layer is made of polyurethane, which is a common compound used in coatings and varnishes. So the Error polyurethane interface has an index of reflection of 1.5, from which we can deduce F0. And that's just the equations for index of refraction.
Okay, so they use a constant, so you don't need to calculate the Fresnel term, basically.
But you still have to, right? Isn't that just the...
Oh, yeah, you still need to calculate the Fresnel term, just they use the constant for the F0.
Okay, and that's the reflectance at normal incidence. So that's what's reflected right back at the if the ray comes in at normal incidence, I guess, along the normal. Or yeah.
I think that's right.
Okay, and then so we've got integration in the surface response. So because we must take into account the loss of energy caused by the additional clear coat layer, we can reformulate the BRDF from equation 1 like this, where FC is the Fresnel term of the clear coat BRDF and FC is the clear coat BRDF.
What is equation 1? Is this just F equal to FD plus FR or something like that? Because diffuse plus specular.
Yeah, we've got FD and then we've got FR and then FC.
Yeah. I guess it makes sense. Then 1 minus Fresnel term means like if it is not reflected by the clear coat layer, then it enters the base layer, right?
Okay.
And FC has the Fresnel in it, so it should cancel out.
Okay, then that's what
Yeah, so it's actually a lerp, but the Fresnel term in the FC is kind of like already inside FC.
Yeah.
Okay, so we've got parameterization of the clear coat layer. That's the clear coat material model encompasses all the parameters previously defined for the standard material model plus 2 more. We've got clear coat, which is the strength of the clear coat layer, scalar between 0 and 1, and the roughness value, which is perceived smoothness or roughness of the clear coat layer. And that's a scalar between 0 and 1 also. So clear coat roughness parameter is remapped and clamped in a similar way to the roughness of the standard material. And we see here how clear coat parameters affect the appearance of a surface. So we've got varying strength of the clear coat from low to high. And it's got an increase in the Fresnel and the regular reflection off the surface. And then roughness, I guess, is kind of diffusing that reflection. So we've got GLSL implementation of the clear coat material model after remapping, parameterization and integration of the standard surface response. And that lower end of the clamp is for avoiding divide by zeros, if I remember correctly. So this is the V term we just looked at, and then some other terms from last week, I guess. Okay, so base layer modification. The presence of a clear coat layer means that we should recompute F0 since it's normally based on the air material interface. The base layer requires F0 to be computed based on a clear coat material interface instead of air material interface. This can be achieved by computing the material's index of refraction from F0 and then computing a new F0 based on the newly computed index of refraction and the index of refraction of the clear coat layer. So if we know that that clear coat layer has an index of refraction of 1.5, we can solve for the base material's index of refraction and then compute a new F0 from this new value. So since the clear coat layer index of refraction is fixed, we can combine both steps and simplify that like this. And we should also be able to modify the base layer's apparent roughness based on the index of refraction of the clear coat, but this is something we have opted to leave out for now.
I wonder if the fixing the index of refraction is like a performance thing, or if it's like you don't actually really need to change it much, because it is quite handy to be able to have this formula, I guess. But
It's not a. Oh, you mean to fix it into a constant?
yeah,
I
so
guess
1.5.
it's just simplifies things a lot, I guess.
Yeah,
And also, I guess it's performance also related.
yeah, because it's hard to tell how much of this is because it's focused like targeting mobile.
Yeah. Yeah, I think it's just to get a constant value for F0 of the base material.
I also guess if you have too many parameters, it will like confuse everyone, confuse artists.
That's true. I wonder why they say there that the base layer's apparent roughness should change as well. Because did they have the index of refraction in that original? I thought it was just kind of a like remapping to linear space, right?
Because let's see.
It's just square.
Yeah. So I wonder why having an extra layer changes how the roughness works.
I don't know. They don't explain that.
Yeah. So it left as an exercise to the reader.
Maybe it's a like since it's apparent roughness, maybe that's purely like how you interpret it. Like when you have the clear coat on, it doesn't look right from what you're expecting, or something like that.
Yeah, it's related to human perception, I guess.
Yeah.
It's like the professor that taught my introduction to computer graphics class said the first law of computer graphics is if it looks right, it is right.
Not
Fair
great.
enough.
So we've got the anisotropic model. The standard material model described previously can only describe isotropic surfaces, so that's surfaces whose properties do not change with respect to direction. Many real-world materials, such as brushed metal, can only be replicated using an anisotropic model, which is one where there is a direction dependence. And so, so there's some different surface behavior based on that, because that kind of informs the sort of shape of the microfacets, I guess. So we've got the isotropic specular BRDF previously described. Can be modified to handle anisotropic materials. Burley achieves this in the anisotropic GGX NDF. Which is here. Relies on two supplemental reference terms, which are alpha B and alpha T, which are the roughness to the along the bitangent direction and the roughness along the tangent direction. So there's another paper that proposes a way to derive these two values by using an anisotropy parameter that describes the relationship between the two roughness values, where alpha T comes from the surface roughness, and then alpha B is solved for using some anisotropy term. So the relationship defined in this other paper is different, offers more pleasant and intuitive results, but is slightly more expensive because they've got to take a square root here. And they opted to follow a relationship described in another paper, as it allows creation of sharp highlights. So that's the surface roughness and 1 plus the anisotropy and 1 minus the anisotropy for each term. So note that this NDF requires the tangent and bitangent directions in addition to the normal direction. So since these directions are already needed for normal mapping, providing them may not be an issue. So we get the implementation listed here. We've got so that, they're passing in the AT and AB. So in addition, this other paper presents a nice anisotropic masking shadowing function to match the height correlated GGX distribution. The masking shadowing term can be greatly simplified by using a visibility function instead. And we get this, I guess. And this delta term is the same for every light, so it can be computed only once. I guess that's another approximation that they can use. Or lambda rather. And so they get this implementation. Okay, so then the anisotropy parameterization comes from the this value is the amount of anisotropy, which is a scalar between -1 and 1. No, it doesn't require any further remapping.
What does it mean? GGX correlated. What's the correlation that they're talking about?
This guy here. Yeah. Not. So it's the height correlated GGX distribution. I'm not familiar with that. I guess that's. Yeah. I guess there's a paper that they point to.
I'll check the paper. Thanks.
Is the height correlated just basically talking about, is that just like the name of the G term, I think? Like that distribution that they're using for G, I think they just call that the height correlated.
Because it takes an H term, I guess, maybe. Or H is the half vector, isn't it?
Yeah.
Yeah.
Because of the roughness, I think, is kind of how they do the height, right?
So that's going to be related to the microfacet stuff, maybe.
Yeah, so I don't think they get into what the height correlated means here. It's just, that'll be in the paper.
Thanks.
So we've got some kind of indication of what this term means from low values to high values. Or I guess there's more of a sort of a smearing effect as you go to higher values. Kind of you get more direction dependent behavior with that. We have a couple of to-do sections.
So the anisotropic stuff is basically just modifying both the G and the D terms to have two different roughness values per direction, and then kind of just lerp, or may not lerp, but interpolate between them somehow, right? Is that kind of seems to be what's happening?
It's got some dependence on yeah, like the surface tangent and bitangent. Yeah, so I guess they're yeah, kind of indicating what the geometry of the microfacets are. For I guess they mentioned brushed metal, so I guess that's typically got grooves in a certain direction. So
right,
look at that from
yeah. So there's like on the surface, whatever the tangent and bitangent are basically telling you how much of each direction's roughness parameter to use, and then they're kind of mixing those together. Does that sound right?
Seems reasonable to me.
Okay.
Yeah, so because they're yeah, I'm not exactly sure.
Yeah, it's hard to interpret all the math just on the spot.
Because I think that's tangent dotted with the h vector, and then you get the bitangent dotted with the h vectors. So I think that's how they're scaling those.
Wonder why. So they have the bitangent roughness multiplied by the tangent dot the h vector, and then they have the tangent roughness multiplied by the bitangent's dot product. I wrote that. That's in the code snippet, the EGGX one.
Yeah, I was just trying to look and see if I could figure out if they mentioned anything about it. Yeah, I'm not sure. It could possibly be a typo.
I don't know. Probably not. Like what? And then I'm looking at that A2, and it's just the two different roughness multiplied together. So I kind of have no idea what's going on there.
Yeah,
something like the cross product. except that it's like one-dimensional.
Oh. I'd believe that. Oh, actually, yeah, I see that the equation 41 talks about this. So I guess they kind of just treat that as a fact, and you go from there.
Okay. So I guess 4.11 is not implemented yet. Do we want to do 4.12 or?
We can stop it here. And
Okay.
the 412 is long.
Okay, they're starting to look at cloth behavior. Yeah.
It's interesting. I mean, maybe there's a reason for it when you actually get into 412, but it's interesting that the cloth model is separate from the rest of it. I would have thought that the PBR method would be enough, unless this has like more complicated inner surface interactions or
Yeah, I
something.
think so far everything so far can be implemented in a Uber shader kind of thing, Uber material. But for the cross, it's kind of different because, as the paragraph says, it's often made of loosely connected threads.
Mm.
So
Yeah, actually, just
crisscross
briefly
pattern.
glancing at it, it seems like a lot of it's like subsurface scattering kind of stuff. So that makes sense. I guess theoretically, in like a offline render, you could probably have a PBR model that has all of the subsurface scattering and everything kind of built in, so that like the clear coat and the cloth could probably be described for free with that. But I guess that's probably too expensive for real time.
If all else fails, I guess you
yeah,
could.
that's why they cheat.
Right.
If all else fails, I guess you could have geometry for the individual threads. So,
Oh boy, I don't think that would work well on Android.
a little bit brute force that way, I think.
Expensive even for offline.
Yeah. Oh, cool.
We can have geometry for every macro facet.
Maybe with nanite, right?
Yeah.
I wonder if they are actively planning on doing the subsurface model chapter, or if that to do is like a permanent to do.
Yeah, I'm not sure. I haven't seen any revision history on this. So I guess I'm not really sure what their intention is with finishing it. We've got a couple of papers. I haven't looked through this yet. So we've got Eurographics 2022. Something I'm not sure if they mentioned, but the revision demo party was this past week. There was some cool stuff if you guys are into competitive live coding stuff.
Sounds cool.
Yeah, I'm not sure if I watched some of it on Twitch. I don't know if there's any recordings anywhere. I didn't find any when I looked the other day, but I didn't look very hard. Yeah, so we've got some stuff about deferred texturing in Horizon Forbidden West. We got permutation coding for vertex blend attribute compression.
Oh wow, 13 skinning weights per vertex compressed into 64 bits. That sounds impressive to me.
Yeah. That's for animation
Exponentially
stuff.
better rotations. What's that?
Oh, I read that briefly. It's basically what's the word for it? Like geometrical algebra or something.
Oh yeah, geometric algebra.
Yeah.
That stuff is way over my head. I went to a presentation on that one time at SIGGRAPH that was using terms like rotors, and it's like just all right. It's completely
Yeah.
different
So,
type of math.
so I think this kind of gets into that, but limited to quaternions, like describing quaternions in geometric algebra.
Uh, Basically, the reason to use geometric algebra is quaternion is interesting algebraically, but it's not provide any intuition on what's going on.
Yeah, typically whenever I've used quaternions, it's been as a black box with some
Yeah.
implementation.
Yeah, it's quaternion is more like everything in math is basically a set of rules. You describe a set of rules, and for quaternions, these rules just don't make sense, even though it works. So taking the slang shading language from research to production.
Yeah, I'm interested to see that.
Yeah, slang is a good language. I hope I think for it to be really in production, the main thing they need to improve is the build system. Is how easy or how hard you for everyone else to use it.
Is it just like a complicated process? Because shouldn't it just be like you just pre-process your shader basically, right?
That's my understanding.
Yeah, well, I tried to build the project and I failed in a day. So
Okay, fair enough.
it's not easy. It's like a typical research project. Also, for typical research project, they probably consider other platform. That's another thing. If they develop on Windows, they probably won't care about Linux.
Right.
So
Yeah.
that's another thing to be solved to be in production.
Some stuff about it, platform independent something or other for a portable interface for heterogeneous computing. And I think I may have liked this Bbh thing. This looked kind of cool. I didn't read through it very closely, but he was walking through methods for creating Bbhs.
Yeah, I want to read this.
Creating BV? Computer shader, or like it's just creating BVH on CPU?
It's CPU, right? I think.
Okay.
Maybe not. It's Float 3.
Yeah, I'm seeing some HLSL syntax here, so maybe for use on the GPU.
No, it looked like C++, so I guess it's CPU.
It's very easy to read sane C++, so... Okay.
Yeah, I want to, in my Rust ray tracer, the BVH implementation is pretty terrible. It's just like I think it's the one they describe in like ray tracing on weekend, where it's like you just randomize the dimension to split everything in half by each time, and it performs quite poorly. So I would like to have a better one.
It performs okay, but yeah, we can do much better. Remember that paper we read about BVH?
I don't actually.
There was like an overview paper we looked at one time.
Yeah, it's just a lot of dimensions to improve BVH, basically.
I should check that out.
Yeah, that's an area I'd like to improve as well, because just I've written a path tracer that does you know, explicit primitives like this. I guess the one I'm working on right now is SDF based, but this, yeah, being able to handle like real meshes would be cool.
Yeah. For SDF based, you can also use Bbhs
You can
as long as you can have a bounding box.
as long as yeah, that's a big if. I guess with some of the fractals.
Yeah, how do you
Yeah.
compute that? Do you just like test a bunch of like points and see if it?
Some have basically infinite domains, so you can't really give a good bounding box. Some are constrained
Yeah.
to some area.
Would you just specify manually the bounding box, or is there a way to figure it out from the equation?
I'm not actually sure. Yeah, I don't know. Because one that I've been playing with, yeah, I guess it would be actually pretty easy to define. Like it's like a tree-shaped thing. I can pull it up really quick. Is that'll make a problem. Love it. All right.
Yeah, Twitter doesn't let you do anything anymore.
Well, in any event, this tree shape is something I've been playing with, and that's so I was using domain repetition, where it's basically repeating on the x and the y, or x and the z rather. And that's just using the SDF method of modding the x term and the z term by some amount.
Makes sense. I love how simple that stuff gets, but then produces these insanely complicated results.
Yeah. Yeah, the fractal stuff especially, it's a lot of fun. Let's see if there's anything else. So we've got another mention of anisotropic GGX, so that's looking at that in a
That's
linearly transformed
related to
fashion.
what we talk about today.
Yeah. Using 4D lookup textures. Oh, something Intel put out, I think today, there's a new version of Sponza that's got a whole bunch of, it's got real high resolution geometry, and then it's got like the banners and things, and a couple other like Ivy models as separate components. Let me see if I can find that really quick. And there it is. Okay. Yeah. So this is love it, love it, love it, love it. Yeah, it's on Intel's website under graphics research samples. Yeah, so they've got a new new version of Sponza, and then it's got
3.4, 3.3 gig.
that's
That's a lot of geometry.
well, so no, that's actually a couple different copies of it. There's based
Oh,
on
okay.
different conventions for X up and Y up or Z up or whatever. And then so then they've got like as separate add-on packages. They've got the colored banners and then some Ivy models, and trees, and emissive candles. Kind of cool.
Animated night.
Yeah. So I guess a lot of these are in GLTF. So Yeah, I was actually looking at that earlier. Kind of, it'd be cool to mess with some GLTF loading. Try and get into some of this.
Yeah.
Good reason to do it.
Hey, would you mind linking that page
Oh yeah,
on
absolutely.
the chat?
If I can get my top bar to come back.
I looked at that anisotropic GGX one briefly, and interesting that they say modern game engines use a linear transform cosine approximation of GGX for isotropic GGX. So it sounds like in most games their PBR model uses linearly transformed cosines in their like base PBR model. I've never heard of that before.
Well, I guess the anisotropic model would generalize to the anisotropic case if you set both terms the same, would it? Or
Well, like this is them adding on the anisotropic, like because they're saying that was a drawback of it is you couldn't use the linear transform cosines for the anisotropic version.
okay.
Yeah, in the abstract there they say there, but I just wasn't aware that games use this as like the main way apparently.
I'm not very familiar with the linearly transformed cosines, how that works.
I guess it's basically just like a replacement to a lookup table, right? Like a cube map or something. Instead of that, you just approximate a function instead. I thought that was kind of cool. They just give you link those CPP files that are just the lookup table.
Oh, yeah, here, yeah.
Like, but it's like margin cube, right? The margin cube algorithm is really easy to implement. It's the main thing is a lookup table.
With
Marching cubes is just kind of handling the 256 cases for, or I guess
Yeah.
I'm not quite sure what you mean. I guess yeah, just if you've got the data, I guess you can just implement it straight from that.
like these lookup tables are just the coefficients, right? Or for the linearly transformed cosines. Is that true?
Seems like. Let's see what they got here.
It's nice though that they just give you the raw values.
5-dimensional array. It's pretty nice. Jesus. Yeah, so I'll probably put that in a set of 3D textures or something. Yeah, because they're mentioning it's 8 by 8 by 8, and then there's some number of them. Okay, 3 sets of 8 by 8 by 64, so they're packing them together. So they can use the hardware interpolation for at least part of it. Cool. So we've got restir for specular bounces. I haven't looked at that. The restir is basically it's some structure for holding a bunch of lights, isn't it? I guess I'm not super familiar with it.
Well, it's like the reservoir sampling, which I guess is a stats thing, but I guess it's basically I think it's like every time you make a approximation, you kind of keep the previous results to improve it over time.
So
I think that's like the reservoir of samples or something.
This is a cool project. Somebody on the GP server has been working on this. It's a sparse volume for fluid simulation. They've got a way to do representing a larger larger volume structure based on much smaller pieces of the volume that only are only the occupied areas. I don't know if they have any visualizations of that on here. Yeah, so they like got an outer bound on that, but then there's a layer below that that's just the occupied. I don't know if they, because they've shared some stuff about this the past couple months, but yeah, I guess there's a more in-depth write-up on it. That's cool. Some stuff on refraction, transparency, blending, and alpha testing from Sem Uskal. This guy's good. Yeah, might be might be interesting. We've got a overview of the pipeline in something called Vortice, an artsy fluid simulator. So they've got like a flowchart of how everything works, I guess.
It's a cool way of explaining it. I like that.
Yeah, because it matched the structure of the operation, I guess. Yeah, that is cool.
It's like a shader graph with comments.
Cool. And so I guess that's what we've got and stuff for this week. Does anybody have anything that they want to share?
Yeah, I guess this article not related to graphics, but it's fun.
That's standard sort for large-scale operations, I guess.
Yeah, it's just going to really deep about optimizing sorting.
Cool.
Oh wow, very. When they say that we are changing it, is that like LLVM's gonna change it, or they are like internally at Google they're doing it?
It's libs C++, so it's the standard library shipped by Clan.
Oh, okay. Well,
Cool.
I could.
That's a what?
I was just saying I could briefly show my dithering thing if anyone's interested.
Definitely.
Yeah, sure.
You want to do that through Discord?
I guess.
I can pull that up.
Sure. Yeah. Well, maybe I should share because I can just run it locally.
Yeah, let me turn off my.
All people can stream.
How do I do this?
You can have people streaming at the same time.
Oh, right. Oh, wait.
Well, I guess pretty well done on my end, I guess. Yeah, so I can just put up the Discord window as for the recording.
Yes.
Yeah.
Okay. Is that streaming now?
Yeah.
Can you see VS Code?
Yep.
Okay,
Diffused
cool.
actual code though.
Yeah. How do you zoom in?
Wait, do you have 2 line numbers?
Oh, it's because it's the diff version.
Oh.
Yeah, that would be. Yeah, so I can just show it running real quick. So here I've just got this collection of album covers from just every time I play a song on Spotify, it saves it. So basically, the thing I'm wanting to do is I have a little project where I show what's playing on Spotify on an e-ink screen, and it's a 3-color one, so it's black, white, and red. And I've been wanting to try to display part of like the red part of the actual album art too, but the problem is when you dither with with a red, white, and black palette. The way the dithering works is, it finds the closest color and then quantizes to that and then diffuses the error around. But it means that if my only 3 colors are red, white, and black, then if you have like a yellow or something, that's probably going to quantize to the red instead of the black or the white. So it just ends up looking really weird where even if the image isn't very red looking, there's just tons of little red dots scattered around. So my kind of idea is to figure out which images have a decent amount of red in them by doing a color like clustering to figure out like the most common colors. And then if one of those is red, mask out all the pixels that match that, and then only dither those with the expanded palette. So let's see, like this one is this album cover is pretty clearly gonna have some red in it. So I can try running it with this. So I've got this command line tool here that I've made so I can specify -n for the number of clusters. So like pick the 7 buckets for colors. And then here's the color I specify to match against to mask out all the colors, all the pixels that are this color or in this color's bucket. So close enough for this color, and then dither them separately. Oops. So I can do this one. And I'd still need to kind of work. Oh, actually, this went pretty fast. But so this it just kind of did it to here. So you can see when I zoom in, it managed to did the expanded dithering palette on just those red pixels. But like I can try a different one with more than just red in it.
One that failed, like you were talking about earlier.
Pardon me?
I was just interested in seeing one that you said you were describing how it failed earlier on ones with not a lot of red in it.
Oh yeah, like some of them just look kind of weird. Like I don't know, like this one, like it grabbed parts of his face too, and like that shouldn't be considered red.
That's a
But
like
if I don't give this, still working on the interface for this, but if I don't give the color, you can kind of see here I just on the left side I put the different color buckets it shows. So I guess for some reason, I guess his face is kind of red, honestly, but so I guess like parts of his face were assigned to this red bucket, so the algorithm took those pixels as well. So ideally, it would do a better job of segmenting it into the different areas, and like maybe the answer is just to look at all the pixels and just look at the color distance for each pixel individually and not do all this clustering stuff ahead of time. I'm not really sure. I'm probably gonna have to try out a bunch of different techniques.
Looks like a film image, and that's something they were talking about. The guy who does the color grading had been taking the color training thing. He was talking about film. A lot of times the colors, the the lower colors, the shadows and stuff, they have a lot of color in them with the with film images. So yeah, I'm wondering if there's any kind of like pre-processing you could do to kind of. I'm not sure.
Yeah, because like the reason why I settled on the clustering part was because I also wanted it so that if there, even if there was red that matches, if there wasn't enough for it to be like one of the main buckets of colors, then I wanted to discount it and just do it in grayscale. So I'm not sure if there's a way to kind of include that criteria as well while still not getting overzealous with the matching. So I don't know. I'll be tweaking this for a while, and hopefully I'll have some good results soon.
That's a cool project.
Yeah, like I just love when you zoom in, like how cool it looks with all the individual pixels.
Have you tried the thresholding, or would that make sense for this type of with the noise pattern, or does that make sense for the way that you're doing it?
The thresholding? What do you mean by that?
Dithering with a noise pattern instead of error diffusion.
Yeah, that'd be worth a shot. Yeah, I should try that. I've been wanting to experiment with other dithering methods. So, because like it's kind of hard to see here. Yeah, so I only have the Floyd Steinberg so far, but there's a bunch of different types. And I've set it up so it's pretty easy to define more. I just have to. This is a bad formatting, but yeah. So all I have to do is kind of add this matrix of weights, and then so I can give it any matrix, and it should be easy to add like all the different variants out there. Because I've definitely seen better results with. I think it's like Atkinson dithering or something is a different set of weights, but I noticed that one gives you a lot better contrast, where like all of the darker parts like stay really detailed.
Oh, so this is how the error is diffused across the image.
Yeah. Oh, yeah. Sorry, I should explain that. So it's like, think of this as like, this is one row. So consider so if you're on pixel, like right here, you would be like quantize it to a specific color, like the best matching color, and then you would know how far off you are by just subtracting them. And then to the pixel to the right, you would give 7/16 of that error, just add on to it. And then in the next row, in this case, it would be like this. So if this is your current pixel here, you give 7/16 to one beside it, and then underneath it, you give 3/16. Underneath to the right, 5/16. So you kind of just distribute the error to the pixels surrounding the current one you're dealing with, and then you move on to that. So that's kind of like how, if you think of like a completely 50% gray image, if you're only dithering that with black and white, let's say on the first gray one, you'd quantize it to like black or something, and then you'd add, I guess you'd have an error of positive 50% gray that you like cut off. So you just add it to partially the pixels next to it. So those might push it, that gray might make them just actually black. So then the error is kind of handled that way.
Okay, so that neighbor pixel is going to have that difference when it's considering the closest color for the next pixel.
Yeah, so if you gave all of the error to the pixel next to it, then it would add 50% gray, and now it would just be actually black. So then there would be no error when you quantize that one.
Oh, and okay, so then these weights weight that contribution. Okay, that's cool.
Yeah. So just by providing different weights, you can get pretty different results. Let me just quickly show you this website. Ditherit is pretty cool. You can just kind of play around with this stuff. So if I give it this picture, you can pick a palette. So I'll just do black and white, for instance, and then they have all these different algorithms. So like here's this Atkinson one. So you can kind of see what the patterns this gives versus the Floyd-Steinberg I'm using. Very similar, but like if you focus on like the hair, for instance, and the Atkinson one, it's actually just pure black. So you get interesting results by trying out these different ones. It'd be an interesting thing to explore whether or not you could decide some criteria for which one's going to be the best algorithm for like a type of picture by like analyzing it ahead of time, but that's like another rabbit hole to go down.
Sounds what you're saying sounds kind of like the BC7 compression, block compression, where it tries a bunch of different block compression algorithms for each block, and then it takes the best one.
Oh, okay. So it actually like tries them all out and then judges it?
Yeah. But
Interesting.
It's really expensive trying all the different ways, but it ends up giving good and fast compression for a GPU.
That's worth considering, actually. Yeah.
But I'm just saying it's similar to that because you're just trying different things and seeing which one's closest to the original image.
Right. Yeah.
I have a good article on the thresholding version. It's I don't know if you want to try that. It's basically what you're doing is instead of diffusing error across the image, you have a threshold value that's defined in a noise pattern, and so you're using that as a threshold that varies across the image, and that helps inform your quantization. So like a basic pattern is a common one to use.
Right.
I have a question.
Statistically,
I know that dithering is used back in the day when EGA was available. Like what are like some modern applications for it? I'm just trying to wrap my head around. Like,
I actually have a good one. So I had low alpha volumes that were giving some banding. So that was kind of like there were discrete levels that my alpha blending result was kind of bending into. And so by dithering that, I was able to get rid of those bands by kind of breaking it up with a noise pattern, basically. This is what it effectively was doing.
Another cool one is their transparency. So like when you want to have a transparent object and you don't want to deal with like actually blending the alpha or something like that, you can just dither it so that like each pixel is the like there is no transparency happening. It's just you're choosing which object to show.
Right. Okay. I see. But then it has to be very high resolution, right? So you don't the people looking at it don't actually see the dithering, or does it matter?
It depends. Like I don't know. Like a lot of games now do it. So like when like a third-person game, when your camera has like a bush between you and the character, it does this dither transparency, and you can often tell pretty easily that it's dithered.
Yeah,
but it doesn't matter. It looks pretty good anyway.
Yeah.
I see.
Yeah, you will sometimes see some per pixel type of artifacts there because it might have like a grid structure to it.
I see. Cool. Thanks.
Games also use a lot of temporal effects temporal anti-aliasing that can hide some of those per pixel errors.
Yeah, because if you accumulate that and you change the noise pattern over time, I imagine you could get a pretty good approximation of transparency.
Yeah.
Thank you. Awesome.
I have a drop off for now.
Cool.
Okay.
Yeah, see you folks next week. Wait.
Do we want to decide what we're doing?
Yeah.
Go ahead and cut off the recording.
So we